right, so let's learn some shortcuts. Okay, if you did those two problems, guys, if you did those two problems, you clearly saw that it's annoying. Hopefully, if you did them, you got this. If you did this, you got -4 for your answer. You'll notice it wasn't a formula, and if you really think about it, shouldn't that make sense? That the slope, which is what a derivative is, of a line is always -4. You don't need a formula. It's always -4. So if you got -4 here, great. Over here, you should have gotten 6x as your slope. When everything canceled, that's a formula. So your derivative would have been 6x there. But I want to talk about why those, not why, the why is this. I want to talk about some shortcuts so you don't have to do this ever again. Okay, so the shortcuts, and there are proofs for all of these, which we're not going to get into. I won't even be able to show you them this year because we had to cut out some extra stuff. I'm always pushing the limit on what I can get in. And the last couple of years, we've had a little extra time, and I've talked about what we call implicit differentiation. And implicit differentiation, if you learn that, it allows you to see the proofs of these power, product, and quotient rules. But what we're going to do is just talk about the rules, and that'll still put you in great shape heading into either AB or BC. In fact, again, like I said, what we do today will be all regular pre-cal does. Typically, they don't even get into the chain rule, which we'll do tomorrow. In fact, this year they might not even do derivatives at all because they're going to be further behind than we are. So anyway, let's talk about the power rule. Now, I have put the rules here, and as you're glancing at them, they probably look a little overwhelming. So I'm going to try to simplify them in some ways that's going to be helpful to you. Okay? Now, we said yesterday that there's a lot of different ways to write a derivative. As we're starting out, what we're going to be doing, when I'm not going to say this word beyond today, but we're going to be doing explicit differentiation as opposed to implicit differentiation. Now, the difference is explicit, they are functions. This is when y is written explicitly in terms of x. So when you have functions like y equals blah, 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 blah with a bunch of x's, those are explicit equations because one variable is written in terms of just another. Things like circles, where you have x's and y's mixed up together, right? And they're all on one side. Those are implicit functions, or not even functions, implicit equations. And implicit, you would need to know that thing I talked about, implicit differentiation. We're not doing that. So everything we're going to do on functions this year is going to be y equals stuff, which is going to be a little bit easy on you. And then we'll let calculus take you to the next level. Okay, I'm assuming most, if not all of you, are taking calculus. Okay, so we have y equals. If your function is nothing but an x raised to a power or an x raised to a power with perhaps a coefficient in the front, if that's it, then and by the way, it could be a bunch of these added or subtracted together, not multiplied or divided, but if you have a variable like an x raised to a power with maybe a coefficient, if you have that or multiple of those added or subtracted together, you can use the power rule. Okay, and the power rule, all you have to do, take whatever the power is, multiply it by the lead coefficient, and write it down. So you can see I went n times 1 is n. Then you just drop the x, and then take the power and decrease it by 1. And that is a shortcut for taking the derivative. And because it is the derivative, we have to label it as the derivative of f. And we do that by going f prime of x. And if there happens to be a coefficient in the front, you take that number n, multiply it by a, and a times n is something. Write it there. I just put a times n because I didn't know what they were. And then drop the x, and then take the n and decrease it by 1. Okay? Now, technically, and Leibniz talked about this. He's the other guy that helped invent calculus. Technically, what I'm also doing, but I'm not showing you this here, but you may see this later on. Not this year, but maybe next. Well, actually, you will see this later on tomorrow. But technically, what I'm also doing is then taking the derivative of x with respect to x. But what's dx do you think? 1. So technically, that would cancel and go away. Okay, so what we're doing, if you notice, I'm not really doing anything with the x, I'm only working with its power. But technically, if that x was something else, if it stood for some other value, I would go back at the end and multiply it by the derivative of the x. But, and you'll see this in a second, dx is 1, so I'm not bothering to write that today. Okay, same thing over here. N times the a is an. By the way, another way to think about it, if it is a constant that's being multiplied by something, you can just drop the constant down and then start the process. You'll notice that nx to the n minus 1 is the same thing as nx to the n minus 1 if I just drop the a down. So sometimes you won't have a power and you'll have this constant that's being multiplied out front. You're welcome to just drop the constant down, put a times, and then start your derivative process. Okay, that's if you have a constant multiplied. And you're going to get lots of practice with this. You're going to like this. So if your head's spinning at all right now, don't worry about it. You'll be fine. Okay, so that is the power rule. And again, you can use the power rule as long as you have a variable to a power, and you can have a bunch of those as long as they're added or subtracted. And if they're added or subtracted, you just do one derivative, the next derivative, the next derivative. But that you cannot do this if they're multiplied or divided. So if you had something divided by something else, completely different rule. But as long as they're added or subtracted, you could just do each one of these individually and move your way through. Okay? Now, I want to get down to stuff like a variable that just has that doesn't have a power, just like a variable like 5x. So if you had a function like 5x, think about this rule. For me to take the derivative, I would take the power, which is a 1, multiply it by the 5, copy the x down, and decrease the power by 1. But what is x to the 0? So what's the net result of this? I just get the coefficient. Now that should make sense, because isn't 5 to the x a linear term? Like if it was 5 to the x squared, that would be a quadratic term. But 5 to the x is a linear term, right? Do you think about it just by itself? And what's the slope of a linear term like that? It's the coefficient, right? That's the m. So if you ever see something x, the slope is just going to be the coefficient. Now with that in mind, what if you see something like just a constant? What do you think the derivative of a constant is? Well, guess what? A constant is also a linear term. How do you graph y equals 7? It's a horizontal line, right? What's the slope of a horizontal line? 0. So the slope of that is 0. Now, if you're wondering, how do I get a derivative from here to here? Well, technically, isn't 7x to the 0? You really think about it? So if you're really thinking about it that way, 0 times 7 is 0. Decrease it by 1 doesn't really matter because 0 times anything is 0. So rather than making your life ugly, when you're dealing with the power rule, whenever you're dealing with a single x, you're just going to get the coefficient, because if you think about it, that is the slope of that linear part. And whenever you're dealing with a constant, the derivative of a constant is always going to be 0. And remember, the constants show up not just like numbers like 7 or -10. They also show up like pi. Pi looks like a variable because it is a Greek letter, right? But it means a constant, 3.1415926, whatever. But then also e. Do you remember what e is? E is about at 2.17 or 2.718, blah, blah, blah. So it also looks like a variable, but it's really a constant. So be careful about stuff like that. If you know it's a constant, the derivative of a constant is always 0. So let's take a look at a couple of these real quickly, and then we'll move on to the product rule. So we'll start with some basic ones. What about this? If that is the function, then to write the derivative, I would say f prime of x, and be really good about labeling it. Don't just write the derivative down, because if you just write it down, the AP reader is going to go, what is that? Always label what you're writing. So the derivative of f is, or f prime of x is what? 6 times the coefficient would be 6. Copy the x, decrease it by 1. And that is your derivative formula. So this graph, which is x to the 6, which looks a lot like a parabola, but goes up a little quicker. That right there, if you want to find the slope at any point, you use this formula. So you could just plug in x equals 1 or x equals 2 or x equals whatever, and you would know the slope there. All right, what about this one? Can I use this power rule on this thing? Yeah, because it's added or subtracted, so each individual term I'll do the power rule. So let's try it. F prime of x, what's the first one? All right, 12x cubed, y'all see that? Next one, minus 6x squared. Next one, plus 10x to the first, right? And then what did we say about something with an x? It's just that because that's like a linear term, right? So the slope would have been a -8. And then what do you do on a constant term? Goes to 0. All right. What about something like number 3? Number 3, the derivative is, yes, 4 times a half is 2x cubed. Next, minus 6x to the first. And then constant goes away. What about 4a? What's the derivative? 0. It's a constant. What about 4b? It's tempting to write 4e cubed, isn't it? But what's e? It's a constant. What's a constant to the 4th power? Another constant. What's the derivative of a constant? See how sneaky that can be? Same thing with 4c. What's the derivative of that? 0, because pi and e are not variables. They're in math, they always stand for a number. Okay? So that would be also 0. And by the way, it goes back to, remember what I said about the x? That technically you're right, you're taking the derivative of the x with respect to x, but dx cancels. So if you had really applied the rule here, this is what you would have done. You would have gone 4e cubed, but then you would have said, what's the derivative of e with respect to x? Well, the derivative of e, because it's a constant, is 0. And all that goes away and gives you 0. So technically you could say 6 pi squared, but then you got to go back and go, what's the derivative of pi? 0. Well, if that's the case, then it's a lot easier just to remember, if it's a constant, the whole thing is going to end up being 0 every time. So why bother with that extra process? Now, a little bit trickier on these last two, because I'm going to throw a slight curveball, or this last one, I'm going to throw a curveball at you. So what about number 5? Can I use the power rules here? First term. So 10 out front, there's already a 1/20th technically. So 10 times the 1/20th would give me f prime of x equals 1/2 x to the 9th. Next term would be negative 15x to the 4th. Now what about these? Can I do the power rule on these? Now currently I can't because the power rule requires x to be in the numerator. And right now x is in the denominator. Can you do anything about that? I could rewrite that x on the bottom, x squared, as an x to the -2. And I could rewrite that x to the, I could leave the 2. The 2's fine. I could take that x to the 4th and make it x to the -4. Now, I'll show you another way you can do those also, but I think this is probably the easiest. So now, what would the derivative of 3x to the -2 be? And stick to your rules. What do you get? Take a shot. Don't be afraid. -6x to the -3, because you're always subtracting 1. Good. And then the next term, you're multiplying a -4 by -15 halves. So positive 60 halves, so 30. 30 what? X to the -5. And don't be afraid of leaving those exponents negative. AP doesn't care. I know some people are like, wait a minute, you told me I always have to make them positive. Technically, I didn't. I said when you're dealing with negative exponents, either make everything positive or leave it in everything in the numerator. And you do have all the variables in the numerator, so you're good. Don't feel the need to bring them back down. All right, now starting with number 6, you'll notice I can't do this anymore because now instead of having a bunch of terms added together, I do have added together here, but I also have multiplied by this. Okay, so this requires a product rule. Now there are some of you right now that go, well, couldn't you just spoil it out? Yes, you can. You can just FOIL this out. But tomorrow, when we get to the chain rule, I'm going to have a 5 right here and a 9 right here. And you're not going to be able to raise that to the 5th power and that to the 9th power very easily. So you're going to want to know the product rule. So tonight, don't FOIL it out before you get started and then take the derivative, or you won't be getting practice on the product rule. Okay? So trust me on that. And let's see if we can apply this product rule. Now let's go look up top. What do you do when you have a function? When you have a function which is basically a function times another function. And you can see that down in number 6. This function is this function times this function. And you know there are two functions because you have two different things. One has an x in it, the other one has x's in it. Okay? So when that happens, it could be something like a polynomial and then something like a trig function. It could be something like a polynomial and something like a natural log. But if you have two different things and they both have x's in them and you're multiplying, that's going to be a product rule. And you'll get lots of practice on these. These are not a big deal. So let's take a look at the product rule. The product rule says, if you have this function and this function, the derivative is going to be the first function times the derivative of the second plus the second function times the derivative of the first. Okay? Now, the way I think about it is I think, okay, if you have a first and a second, just go for the derivative, first d second plus second d first. First d second plus second d first. Now, because you're adding these, it really doesn't matter the order. As long as you have one and then the derivative of the other, and then the other and the derivative of the one. As long as you have that, the order doesn't matter, but I like it. I always put my keys in this order. It'll make it easier on you if you learn like this. First d second plus second d first. So let's check this out. So if I have problem like number 6, and I want to take the derivative, what do? First, so copy the first down. There's my first. Then I'm going to go times the derivative of the second. So I'm going to put another parentheses. And what is the derivative of this? 3x squared plus nothing. So I'm going to put that. I'm going to underline it right there so you can see that's the derivative part. So this is first d second. And then I'm going to say plus. Then I'm going to copy the second part down. And I'm going to go times. And I'm going to go, what's the derivative of the first part? And the derivative of the first part is 2x plus 2. And that goes here. First d second plus second d first, and we're done. We're not going to do any simplifying on this test like this. I might have one problem where you have to simplify, but we are not going to mess with that. If you do, you are wasting your time right now because none of my keys have anything simplified on. All right, we're just working on the method right now. We'll worry about simplifying later when we get the hang of all this. All right, what about this one? Number 7. What do you see? A function times a function. Okay, so for me to take the derivative, looks like I'm going to have to do a product rule. Now, when I go to this product, what's the rule? First, so I just literally just copy it down. And then d second. What's the derivative of the second part? Just 5. And then plus, copy the second part down. 5x minus 1. And then what is the derivative of the first part? Be careful. Negative 6x to the negative 3. Good. And then minus 4x and the parentheses. First d second plus second d first. We're out. All right. Now what about number 8? What do you see? I see where I'm dividing two functions. Well, that's not a product. That is a quotient. Now, every year I have somebody say, well, couldn't you just take the x plus 1 and bring it up and make it an x plus 1 to the negative 1? And now you have a product? Well, you could, except now you also have a chain rule. We haven't talked about what to do when you have a function, an entire function, not just an x, but a whole function to a power. That's something we'll talk about tomorrow. But I think it already took you one step to do this. It's only one problem to do the quotient rule. It's not a big deal. So to me, you're wasting time doing this. Every now and then I'll have somebody do it. Most of the time your answer will not match what AP has. So to me, you're making your life harder than it needs to be. You think you're doing yourself a favor, but you're not. So just force yourself. If you see a quotient, to apply the quotient rule. You'll be happy when you get through this. It's not a big deal. So let's check out the quotient rule. Quotient rule says, all right, if I have a function that's made up of two functions where you're dividing, now watch it. It says, I'm going to take the bottom function, that's the bottom one, times the derivative of the top, minus the top times the derivative of the bottom over the bottom squared. Now that seems like it's a little harder to remember. So here's what I do. I call the top the high and the bottom of the low. And I say low-d high minus high-d low over low squared. So low derivative of the high minus high derivative of the low over the low squared. And if you want to help remembering that, just remember that Heidi is very polite and always goes last, which is stupid, but you might actually remember that sentence. So if you ever get confused and you're like, wait a minute, is it low D high or high D low? High D always goes last because she's polite. Again, I taught one Heidi. She was actually not polite. She was from Russia and was kind of unfamiliar with social norms in the South and was kind of a punk. But anyway, Heidi goes last. Are y'all with me? Hopefully she's not going to check out my YouTube page. Many years ago. All right, so let's check it out. Remember, low D high minus high D low over the low squared. So here we go. I see a quotient on number 8. So the derivative, is everybody still labeling the derivative each time you do it? F prime, F prime, F prime. Remember to do that. Okay, so here we go. You're going to have a big fraction, so you can go put that out there. You may have to extend it from time to time. Here we go. Low, x plus 1. D high. What is the derivative of just that top part? 1. Now I'm going to put the 1, but you don't have to put the 1 if it's just 1 because you're multiplying by 1. Minus, low D high, minus high, x minus 2, times what? The derivative of the low part, which is also a 1, over the low part squared. And again, we are not cleaning these up. Check out number 9. F prime of x, the derivative is, again, I look at it and I see a quotient. Low, x squared plus 4. D high. One minus x minus 5, the high, times 2x, the low, over the low squared. And by the way, do you see the importance right here? What happens right here if I forget to put that x minus 5 in parentheses? Is the math wrong? Yeah, because with the parentheses, I've got to multiply the 2x eventually by both of those numbers, and I got to negate both of those numbers. If I don't put the parentheses, then I don't distribute the 2x, do I? You might remember to, but it doesn't look like you're going to remember to on my end. So you have to get those parentheses around these. Now, around a monomial, like if I happen to forget it around the 2x, well, the 2x is just a single term. So I don't really need them there. But it's a good habit to get into. It's not bad to put them there. So I kind of get in the habit of putting everything in the parentheses, and then I don't have to worry about it, whether it's a binomial, a monomial, or whatever. All right, what about this one? Number 10. The derivative is low. Copy the low down. Times what? 6x minus 3, good. Minus high, copy the high down, times 4x minus 2, the low. All of it over the low squared. And when you look back, low d high minus high d low over low squared. And we are not simplifying any of that. And what is it? What are we doing again? We're finding the derivative, and what is the derivative? It's an equation that gives us slope. So do y'all have any idea what this function that looks like? Yeah, you do. Tell me something you know about this function. Horizontal asymptote is 3/2, so you know it's sliding out to positive negative infinity. Now, I don't know that this factors, but if you put it in the quadratic formula, it might have some roots that are real. So it might have some vertical asymptotes, right? It's possible. So it's some rational function. So it's all over the place. It does flatten out. But I'm guessing, what do you think happens if I plug x equal 100 in there? Way to the right. What do you think the slope's going to be? Nice. He said almost 0. Why is that? Because it's approaching an asymptote, so it's getting really flat, right? So way out there at 100, this thing's getting really flat, either from the bottom or from the top. I don't know. I'd have to figure more out about it. But way out there, it's getting really flat. I bet it's really close to 0. Are you with me? So this right here, I have some insight, but that's a slope. If I really wanted to find the slope at, say, x equals 3, I'm going to have to cowboy up, I guess, and plug a 3 in there and crunch all that ugliness. And that is something that you'll probably do once or twice in this test. But when I do, I try to pick a number that's a little bit nice to you, like maybe the derivative when x is 0, because it makes the math a little bit easier to clean up, or maybe the derivative when x is 1. I'm not going to give you the derivative when x is 100 and make you suffer. Okay? All right, what about these? What do you see on that you could do on number 11? You got two options now. One, you could use what? The power rule. How would you be able to use the power rule? You'd have to move that up and make that an x to the negative 2 before you got started. And then what would your derivative be? Negative 6x to the negative 3. Okay, that's one option. What's another option? I'll rewrite it. Don't you have a number divided by a number? If you have a number divided by a number, can't you do a quotient rule? All right, let's try it with the quotient rule. What's the rule for the quotient rule? Low, d high. What's the derivative of the high? So do I even need to write that part? Okay, so low d high is gone. Minus high d low. What's the derivative of the low part? 2x to the first over what? The low part squared. Simplify that for me. What do you get? Negative 6 over a x cubed, because one of those x's cancel. Simplify that, and what do you get? Negative 6 over a x cubed. So you can do it either way. I got to be honest with you. I a lot of times will just do this. I'll do the quotient rule, but if you like just swinging it up and then taking the derivative, totally fine. But this low d high, anytime the high is a constant, it's going away, so you can basically pick up with the minus high d low over low squared. But it's your call. I'll just leave this one there. What about this one? Now this is what starts getting a little tricky for you. And again, the temptation for tonight is going to be, oh man, I got a product inside of my quotient. Ooh, that could get ugly. I'm just going to FOIL it out. Well, listen, if you had this problem on the test and you multiplied it out first and then did the quotient rule, that's fine. But again, what are you going to do if that's 2x minus 3 to the 10th? Can you multiply the 5x squared in? Not until I do the exponent. Do you want to raise that to the 10th power and do the 10th row of Pascal's triangle? I don't want to take that down to the 10 row at all. So I'm not going to do that. So again, I want you to get a little practice with this, but let's see if we can follow the rules. Now, first thing you do when you're taking a derivative is you always deal with the function. You kind of look at the function, you go, all right, there might be some stuff going on inside the function, but what property is involving everything? See, the product rule is not involving everything. It's only involving these two. But what's involving everything? The quotient rule, because you've got a high part and a low part. That involves everything. So let's start with the quotient. And when I get around to the D high, what's the D high going to be? A product. So you're going to look at this and you're going to go, all right, low D high minus high D low over low squared. You're going to have that set up. And when you get to the D high part, you're going to insert the product rule into the quotient rule. Is that making sense? So check it out. I'm going to leave myself some space here. So the derivative of f is, and here we go. I know it's a quotient rule, so I'm going to put a big parenthesis. Here we go. Low. Copy it down. Now, in purple, I'm going to do D high. So the D high is a product rule, isn't it? So I'm going to put a big parentheses in here and leave myself room for the first D second plus second D first, and it's going to be right in here. This whole thing right here is going to be my D high. So here we go. First, D second, 10x, plus second, 5x squared, D first, 2. And that whole thing has to be multiplied by the 3x minus 2. So I have to put the whole thing in parentheses because my rule is minus, then I bring the high part down, which is both parts of those, times the D low, and then all of that over the low squared. So take a look at that. Low times D high minus high times D low over the low squared. And again, yes, it would look a lot better if this was a test question and you just went, I'm just going to call that 10x cubed minus 15x squared, and then I just have a simple quotient rule and do that. Yeah, if I had to simplify, I would do that too. But you're not going to be able to do that starting tomorrow because I'm going to be putting powers on these things, and you're not going to be able to raise them to those powers to be able to do it. So I'm trying to give you practice today before we get to the chain rule on how to deal with this kind of stuff. All right, what about this? Can I use the power rule on a square root? Yeah. Now I'm going to show you something, and you're going to see this power rule the way we do it, but then I'm going to try to get you not to do it this way. Now, if it's cube root, yes. Fifth root, yes. But square roots show up all the time, and they're always simplified, and if you can learn this trick, you're going to be in much better shape. And it's going to be really better, maybe better to learn this tomorrow, but I'm just going to start with you today. So here we go. F prime of x. Now, for me to take the derivative of this using a power rule, I'll have to convert that square root into a power, right? And what does that give me here then? That's x to the 1/2. So let's try the power rule. The power rule says power times the coefficient, which would just be a 1/2. Copy the x and decrease it by 1. Now what happened? Negative 1/2? You with me? Now technically, I would go back and multiply by the derivative of the x. So tomorrow when you learn the chain rule, when there's more than just an x in there, like when there's a x cubed minus 5 under there, you would have to go back and multiply by the derivative of that. But today we don't have any of that, right? The derivative of x is what? Is 1, because the coefficient of x is 1. So I don't have to ever worry about that today. You'll see the chain rule tomorrow. There's this extra step that won't be times 1 most of the time. Now, if I had to simplify that, what does the 1/2 mean? Square root. What does the negative mean? It's on the bottom. So if I were to take this, I'm going to leave that 1 on the top. I'm going to leave the 2 on the bottom. And the 1/2 means square root of x. The negative means move the square root of x to the bottom. I would get this. Here's what I want you to remember. When you are taking a derivative of a square root, the shortcut for this, the shortcut for square roots double the square root, put it on the bottom. Just literally go 2 times whatever you see. And there is one other thing you have to do. And you'll see this tomorrow with what we call the chain rule. Take the derivative of the x, put it on the top. And you'll see that it's called the chain rule. We don't have to deal with it today because we're only dealing with x's. And what is the derivative of x? 1, and that's why there's just a 1 on the top. But today it's going to seem like the rule is just double it and put it on the bottom and call it a day. What you're really also doing is taking the derivative of that and multiplying by it, which puts that on the top. Now, this rule does not work with cube roots and fourth roots. But in AP Cal, you rarely see cube roots and fourth roots. So when you do, then just do them the way you initially did this. Change them to a 1/3 power and just do them that way. Because it's probably not worth learning the rule for all of these. The rule starts morphing. And you can come up with your own rule if you want to and show it to me tomorrow. But to me, it's worth memorizing it here. It's not worth memorizing it anywhere else. So here, what would you do for the derivative? 1/3 x to the negative 2/3. And technically times the derivative of x, which is 1. And then here, what's the derivative? If that could be written as x to the 1/5, what would the derivative be? 1/5 x to the negative 4/5, because I'm subtracting a 1. So you'd have to find a common denominator, yada, yada, and get there, I guess. All right, now number 16, the last thing. There was a time when I used to teach derivatives where I made people, a little bit out of ignorance, I made people use the product rule when there was 3 things. When there's 3 things, I said, well, we don't have a rule for 3 or 4 or 5 or 6. So what we have to do is pretend like there's 2. And the only way to pretend like there's 2 parts, a first and a d second, is to do what? Group 2 of them together. So I said, okay, I'm going to leave this one maybe by itself and then group these and call this my first part and this my second part. And what I would have them do is go first, d second, and what do you think I would do when I do the d second? Another product rule, and then I would go plus second, d first. And then I noticed when I was done, if I multiplied it all out together, what I ended up with was kind of like this. Let me show you. Pretend that those 3 functions are like a, b, c. Okay? What I noticed when I was done is I ended up having this in no particular order. I had the derivative of a times the b and the c, and then I had the derivative of the b times the a and the c, and then I had the derivative of the c times the a and the b. Do you see what happens? It's really a lot like just having a and a b if you think about it. If I just have 2 parts, my derivative is a times the derivative of the b times the derivative of the a. Bottom line, I'm taking the derivative of one, copying the rest, taking the derivative of the other, copying the rest. So I'm taking the derivative of one, copying the rest, the derivative of another, copying the rest, the derivative of the final one, copying the rest. So the product rule can work like that for 2, for 3, for 4, for any number of them. And it's a whole lot better than this grouping crap. So what we're going to do, and by the way, if my keys still are grouped funny, let me know. Maybe I'll give you a bonus point. But I want to fix that. I think I fixed most of them. But some of my keys were made a while ago. So check it out. If you're doing, by the way, it doesn't matter the order. So I normally start with the first. Maybe I don't normally do this, but one way to do it is just start with that one and take the derivative of this, which would be what? Right. 6x minus 4. Copy the other 2 down. Okay, so that's the derivative of the first one. Then put a big plus. And then what? Copy the derivative of the second one. Or take the derivative of the second one, which would be 6x squared. Copy the first and the third. So derivative of the first, derivative of the second, and the other ones. And then finally, derivative of the last one, which would just be 7. And copy the first and the second. And the order on these is not important because you're adding them all, right? And if you're adding them all, the order in which these three show up don't matter. And whether they're first, second, third, that doesn't matter either. As long as you have the derivative of one of them, the derivative of the second one, the third one, whatever, and then the other ones that aren't taking the derivative of in some kind of form or fashion, you're good. And rarely do you see this, and never do you see this. I've never seen something like this in the AP test. What I do in derivatives is really going to make it where you are immune to derivatives. Like the derivatives will be so easy for you, hopefully, by the end, that anything you see in calculus on regular simple derivatives will be child's play. All right? I think that's all I have. Your job tonight, I believe, is just the homework, power product quotient. Shouldn't take you very long, and I would encourage you to check your work. If you get off to a great start today, tomorrow is the most important rule out there, the chain rule, and it can get a little tricky with the chain rule. You don't want to be struggling with any of this other stuff once you get to the chain. All right.